Well, this is another part of my basic series. Remember last time we did some engine basic stuff and some fun, and I'm going to shoot for engine performance principles this time, basics, and I got a story to tell you at the end of this, and then next week, if things go like I want them to, I'll have a part 2 that I can share with you. That's an addendum to this. If I put them both together, the video would have been too long. But underneath everything, you got basically this breathing machine that takes fuel and air and creates power by energizing the, in other words, it takes the energy that's in the gasoline. A cup of gasoline's got the explosive power of a stick of dynamite. So you atomize a little bit of that and you put it in there and you mix it with this oxygen and nitrogen in the air. And basically the oxygen unites with it whenever the spark happens, and that superheats the nitrogen, which is inert, and it pushes the piston down, and that turns the crank, and that's where you get your power. Atmosphere comes in, fuel is mixed with it on the way in, usually, unless you're gasoline direct injection, but you're still mixing fuel and air, atomize it. And so you got 21% oxygen, 78% nitrogen, 1% other stuff. You know, where does the CO2 that's such a problem fit into all this, huh? Well, where it does fit in is whenever it comes out of the tailpipe of a car that's running right, that has the emission controls functioning, it feeds the grass grows, and they have to mow the grass beside the road. But power is created. Energy is really one of the things that helps us go where we want to go without having to worry about finding a charging station somewhere, with all due respect to the Tesla lovers. Now, question I used to ask my students is, on a non-turbocharged engine, what makes the air enter the cylinders? Well, you can answer that question by thinking about how you get a straw. You put a straw in your mouth and you can make the drink go into your mouth. What do? You start with your mouth is, a small cavity, and when you seal your lips around the straw and you make the inside of your mouth bigger, and that causes the pressure inside your mouth to be less than the atmospheric pressure sitting on top of the fluid, and the fluid basically is going to follow. It's going to go to where the lowest pressure is. And the air is doing the same thing. Whenever the piston goes down with the intake valve open, it's starting with a small space and making it a larger space, and the vacuum that's created there, the air actually rushes in to fill that vacuum that the piston is creating when it's going down. And of course, then it traps it and then it squeezes it. This is kind of how that works. You remember these strokes in order: intake, compression, power, and exhaust. Intake, compressor. This is two-dimensional, but you can see how it's working, and it's turning that crank, and it's providing the power that turns the torque converter or the flywheel in the clutch, and then that goes into the transmission, and it spins the final drive, and the final drive drives the wheels, and that's how you go down the road. Of course, you're multiplying the torque going through a gearbox and all this kind of thing, so just keep that in mind. Now, capturing this atmosphere, you're going to pull it through an air filter, and you're going to go past the throttle plate. You've got vacuum in the intake in this area right in here, because the cylinders are constantly creating low pressure, and if you restrict that low pressure, you wind up with vacuum here. Manifold absolute pressure is technically vacuum. If you take manifold absolute pressure, if you're going to split barometric pressure, you're going to split it between vacuum and manifold pressure. So if you look at manifold absolute pressure and vacuum and you add those two numbers together, you're typically going to get whatever the atmospheric pressure is on that given day, which varies from day to day. Of course, your throttle plate, like I say, creates the restriction. Diesels, unless they have got a throttle plate that's there to help with EGR flow, diesels won't have a throttle plate, not typically. The mass airflow sensor, a lot of these engines now, for a while they tried to do away with the MAP sensor and replace it with the mass airflow. General Motors had a booger of a time with that in the mid-'80s, and they had those mass airflow sensors, and the engine wouldn't be running right, and you'd whack the mass airflow sensor with it would make the engine change the way it sounded. They eventually went back and had MAP sensors put back on those things, as a sort of a backup to the mass airflow sensor. The MAP sensor is also good at telling you if you have EGR flow and that kind of thing. So if the EGR is flowing, it's going to lower manifold pressure. Manifold absolute pressure, and so it can use that as a feedback to see how much EGR is flowing. Okay, so anyway, 14.5 psi at sea level. It'll be less than that in Colorado because it's a mile high. And then your piston movement. This is the waveform down here. This waveform that you see right here is the waveform that you get with a transducer screwed into a spark plug hole, so that you're reading off of that one and the engine's, running and all that. A spinning engine, if you've got your transducer in there, this pattern won't look like this if the engine's just spinning. It has to be running. So you might want to keep that in mind too. We're capturing that atmosphere, we're filtering it, we're pulling it in there. It goes past the throttle plate. And the sensor, this is a basic sensor package. You got a cam sensor, you got a crank sensor. Crank sensor is really an important one for obvious reasons, but I'll tell you about that a little bit more in a minute. Mass airflow, obviously your throttle plate, like I've already talked about. So your cam and your crank sensor are the ones that are going to have a lot to do with how your fuel injection works, and your ignition system too, by the way. And since the engine controller is monitoring incoming air, any kind of air leak that is downstream of the mass airflow sensor will cause issues. Now, you typically on your PCV system, the PCV is going to get its air, it's actually pulling crankcase blow-by into the manifold, but it has to get air to replace that air that it's pulling out. If it doesn't, it'll cause problems. So they actually put the mass airflow sensor usually now out here instead of right there at the throttle body like it was on a lot of vehicles. And the PCV closure hose will be pulling its air out of this because it's clean air anyway. And so the PCV closure hose, that air that's going through the engine by way of the PCV system is also metered. And you can take the oil filler cap off of an engine and watch your fuel trim numbers change, because if you actually are letting unmetered air in through the oil filler cap. Imagine yourself with a fuel trim problem being caused by somebody having or removed the gasket from the oil filler cap. Wouldn't that be a good bug to plant for your students if you were teaching automotive? All right. Now, before the mid-1980s, the fuel was drawn in through a carburetor. It's got to be atomized. It's got to be in little tiny particles so it can mix with the air. And so whenever the spark causes the combustion event, you'll have what they call flame propagation. You want to burn every last bit of that fuel. Now, premium fuel burns slower. There's some people that like to argue about that, but premium fuel burns slower. And so what you'll have with that is you have some of the fuel doesn't burn and it remains on the head of the piston and on the cylinder head. Over time, the rings will wipe it off the cylinder walls, but over time, that turns into crusty carbon junk that takes up space in the combustion chamber. If you start using premium fuel in an engine that's built to burn 87 octane, you're going to wind up with labor knock, spark knock, because you're going to increase the compression by taking up some of the space in the combustion chamber with ever increasing amounts of carbon, and then you'll wind up in a situation where all you can use is premium fuel because everything else pings, and then it'll get to where the premium fuel is causing a ping. Now, if the engine is built to run on premium fuel, that's a different story. You need to run premium if it's built to run on it. But if that thing says use 87 octane, you're not doing yourself any favors by paying the extra money for that premium gas. And there's technical service bulletins from Chrysler and from Ford that came out back when I was at the dealer that said don't use premium fuel in a vehicle that's tuned for 87 octane. Now, fuel injection atomizes the fuel better than a carburetor, and it gives less trouble over time. The older guys always liked the carburetors because they understood them, but I was always, I was like everybody else. Whenever I was first started working on cars, there were points and condenser, and I understood that. And then when electronic ignition came out, I was sort of mind-boggled by that. But fuel injection came out on Volkswagen Type 3s back in 1968. My dad was working on those, and they had a couple of sets of points underneath the breaker plate in the distributor that triggered the fuel injector operation. Let me talk a little bit about that right there. All right, now GM and Chrysler TBI were similar, throttle body injection. Ford had some throttle body stuff. The GM TBI ran on about 12 pounds of fuel pressure. And on one of those, if you've got one of those and it runs and it feels like running like like catalytic converter stopped up, you need to check the fuel filter, because a clogged fuel filter on one of these old 12 psi TBI systems will feel like the exhaust is stopped up. So check that first before you go after the exhaust on one of those. On the other hand, those central sequential fuel injection systems with the little poppets and the spider under there, those things are supposed to have like 61 pounds of fuel pressure, and if they've got 58 pounds of fuel pressure, they may not even start because of the way those poppets are set up. That's another whole other story. I can do some more on that. Now the port fuel injection has got one per cylinder, and you got the wire harness hooked up. And early on, a lot of the fuel injection systems were bank fired, which means they would, even on a V8, they'd have two different banks. It would alternate, squirting back and forth. On your old Ford 60-pin processor, that was pins 58 and 59. And so then, like in 1986, the Crown Victoria came out with sequential fuel injection, and your other cars, your other domestic vehicles were doing that too. And then everybody went sequential because it was just more exact and precise, and emission friendly and all that kind of thing. But the thing about it is, the basic principle here is the frequency of the injector fire is determined by the crank sensor. So you can actually, if you pick up the speed of the crank sensor, you can hear the injectors gaining speed with it. They'll go click, 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 idling. When the engine speed picks up, they go click, 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 click. But not only are they increasing in their cadence, they're also increasing in the pulse, depending on engine load, temperature, and all that kind of thing. So the timing of their firing is determined by the cam sensor. Typically, the cam sensor will tell the engine controller when the piston's at 24 degrees after top dead center, and at any time after that window, it's okay to squirt the next thing of fuel. Now, I actually came up with ways to set the cam sensors on Fords and on GM vehicles by putting an LED in the cam sensor and turning if it's got a cam sensor that's a Hall effect and not inductive pickup, I could actually turn that distributor to the point, set the crankshaft on 24 degrees after top dead center. You got to do some measuring to do that. Then you turn that distributor, watching an LED that you've got connected to the cam sensor input to the engine controller, and you turn it so that that switch is happening at 24 degrees after, and everything works just like it's supposed to. Well, a lot of people would pull the intakes off of these CSFI engines in these 90s model GM vehicles that had that spider fuel injection. And what they didn't realize was you had to actually set the cam retard offset using a scan tool, because if you didn't, it would bank fire the injectors and the fuel economy go to pot. So if you wanted it to sequentially fire those poppets, you had to set that cam retard offset using a scan tool. Above 1,000 RPM, you turn it to about 0 on most of them. That's another story too. But engine load, airflow, manifold pressure, all of that stuff is used to determine what that pulse needs to look like. And the algorithms in those computers are pretty complicated. That's not something that most of us could do. I know I couldn't do anything with that. Well, this is basically how it's wired. You've got power coming in from B plus through this relay to the injectors, and then the ground, except on Jeep Cherokees that are 4 liters between 87 and 90, they actually had the injectors hardwired to ground, and the engine controller, that old Bendix thing, sent power out to the injectors to trigger them instead of sending ground, which didn't make any sense to me. But anyway, the ground signal comes in through here. I should have drawn that with green. But if you tie into that injector right here, you might notice that this area right here is when the injector has not been energized. So you're reading 12 volts right here. Okay, and I can't draw with my mouse worth a toot. I was trying to make a 12 there. But whenever that injector is energized, this is how long it's energized. It pulls it to 0. When it's released, that magnetic field collapses across that fuel injector winding, very vaguely similar to a coil, and you get a spike that's about 50 volts. And this happens every single time an injector fires. Of course, the drivers and electronics in the computer are designed to absorb that. And then it goes back to the same 12 volts it was before, as long as the injector. So this, you might notice this and this line up. But this, the amount of time it's pulled to ground is how long that's open. And you'll see it. If you ever have that pulse width and you're reading it on a scope, and this is a scope pattern I'm showing you, and you snap the throttle, you'll see this thing get wider instantaneously. I had that fuel injection board that I built that I showed pictures of on here before, where you had LEDs connected to the injectors and all that, and it had a crank sensor and the engine controller all hooked up. You could measure that pulse width using a scope on that board of those injectors and pull that throttle open, and those injectors, that pulse width would spread out because it thought it was squirting fuel, but it didn't have any way of knowing it wasn't on that little board that I built. Now, this is a fuel injection diagnosis story. Remember, the customer's not your enemy, although sometimes they may feel like it. The vehicle is not your enemy. The customer's concern is your enemy, and it must be defeated. And to defeat the enemy, you must find out what the enemy is doing so you can neutralize it. That's basically gathering intel and sort data. Now, some rules haven't changed. Carburetor or fuel injection doesn't matter. An engine needs the proper amount of extra fuel on the first cold start, whether it's fuel injected or whether it's, carbureted. But it doesn't need too much for too long. On the choke, when the old automatic choke, first, whenever I first started driving, we had to pull the choke, and then within just a minute or so, as the engine started to warm up, you'd push that choke back in. If you left the choke pulled out and forgot to put it in, then you'd wind up getting gasoline in the oil, and it would thin the oil and it wouldn't be good for the motor. So within a minute, that choke needs to be open. Now on your automatic chokes, when you tap the gas, it sets the choke, closes it up, fires it up. The choke pull-off will open the choke about 1/8 of an inch, and then within, I'm going to say 60 to 80 seconds, depending on the temperature, that choke is going to be wide open and you're going to be off and running. Now this choke right here is drawn open. You might notice this choke is open and the throttle plate's wide open too. I was going to animate that and do some stuff so that but you get my point. Whenever you close that choke like that, when the throttle plate's closed, you're going to get more, there's a little more low pressure there that's going to draw out of this fuel bowl through this venturi down in there. And so incidentally, when it's idling, all the fuel that's going into the engine is going past the idle mixture screw that goes in, got that pointy end on it under the throttle plate, so you can adjust that, tune it out, and make it run real smooth. But you got a throttle plate here on the fuel injected engines, and so the fuel goes in there like that. But you're going to have more of that. So when the throttle is opened, just like your accelerator pump, if you're familiar with a carburetor at all, if you've got an accelerator pump that doesn't work, what is the engine? It just falls on its face, it hesitates. Okay, so what you got to do, if you ever are able to watch this on a really fast scope that will measure those injector pulses, as you're applying the throttle, you'll see extra injector pulses inserted between the ones that are triggered by the crankshaft. It puts extra fuel in there that way. And so as that throttle is moving, you're going to get extra fuel just because it's trying to act like there's an accelerator pump. Remember, the engine still needs the same thing, whether it's fuel injected or whether it's mechanically done with the carburetor, and it actually does it electronically. The engineers knew that, and that's what that dash pot thing I was talking about 2 or 3 weeks ago, it's the same thing. The dash pot on the carburetor does the same job as the idle air control, holding the idle speed up and then letting it go down slowly when you let off. The engine needs the same thing. It just does. That's all there is to it. Now, some rules haven't changed. Again, that's the same title I had on the other. Too much fuel makes a black cloud and lots of hydrocarbons or a no start and wet spark plugs. The PCM depends on heavily on sensor input to make fuel calculations. Of course, it needs good airflow too, and if the air filter is completely clogged up, you're going to have issues. High fuel pressure, a saturated carbon canister where people were packing the gas, a stuck open injector, a ruptured fuel pressure regulator diaphragm. If you pull that vacuum hose off the fuel pressure regulator diaphragm and gas drips out of it, that fuel pressure regulator diaphragm is busted and it's sucking gas right into the intake. And that can hydraulic lock one and destroy the engine too, by the way. Get enough gas in that cylinder, it won't compress. That piston comes up and hits that gas, it'll just destroy it. All right. Too much fuel can be delivered for several reasons. Now, fuel burns more efficiently the better it's atomized. The smaller the droplets, the better they burn. That's why carburetors gave way to fuel injection in the first place, and that's why GDI fuel systems are replacing regular EFI, because the finer the mist, you can actually, if you have an engine that's got gasoline direct injection on it, the gasoline direct injection not only puts the fuel in there, on the older systems, it would actually put the fuel in there behind the intake valve, and when it opened, that mist would be carried in there. On the gasoline direct injection systems, the engine controller can decide when to squirt that fuel in there, no matter where the valves are, how much to put in there, and how to squirt it in there. They can have a stratified or a homogeneous charge, or a mix of either of those two. It's a good, efficient system. Now, there are problems with it. If you got a gasoline direct engine and you just putter around town on it, it's going to build up carbon on those valves. You're going to have a mess. It's got to be cleaned up. Now, if you drive it pretty aggressively, you don't typically seem to have as much trouble with the carbon building up on the valves as you do if Granny's just going to the store and back. Of course, that causes other problems too. Now, Donnie, my buddy, was gathering data. This is a story here on a high mileage 1990 Ford van that had eaten his lunch for several days, and he had other jobs he was doing in the meantime. And I just happened to drop by there one day. I was already working at the college at the time, and on Fridays I could go visit dealerships and stuff because I didn't have classes. And I went over there, and he was stumped. And he says, it runs really rich when you first start it, puffs a lot of black smoke till it warms up. If it had data stream, he said, I could do more with it. The trouble codes aren't telling me anything. Well, this vehicle was a peculiar limbo period around 1990 where it might have data stream and it might not. He was hamstrung and spoiled in need of a window into the system. Now, he was using the new generation Star Tester, and he was plugging into the VIP harness under the hood, and what he would do is it would ask you what the year model of the vehicle was and all that, because it couldn't read it automatically. And you'd go in there, and when it asked you what kind of transmission it had, why did it need to know that? Well, the reason it needed to know was because if it had an E4OD, which was an electronic transmission, it would have data stream by default, because when they rewrote the software for that transmission, they added the data stream function to it. Also, if it had mass airflow, it would have data stream, because they had to rewrite the algorithms for the mass airflow. But Mustang got mass airflow in 1989, but didn't get data stream until 1994, which was very annoying to those of us that were already used to data stream, and everything else had it except Mustang until 1994. But see, when they first started putting mass airflow on Mustangs in 1989, they didn't add the data stream, even though it was available and they were using it on Continentals in 1988. They should have put it on Mustangs, but they didn't, and that was a level of buffoonery that we sometimes see in the engineering world. All right, so we get into the PCM's head, we can tell what it's thinking about. Now, fuel trim cannot be measured with a scope. You just absolutely cannot take a meter with a meter or a scope and measure fuel trim in any way. You've got to measure fuel trim looking at the scan tool, because that is a calculation that is not measurable outside of looking at into the window into the computer. Knowing what it's thinking is important. In other words, you got to know what the PCM's seeing and what it's doing. Now, if you know which outputs are affected by which inputs, if you've got an output that's not working right, you're going to go back and look at the inputs that will affect that output. That's important. And that was the way I always thought. And it was like, I got tickled one time with my shop foreman, because his whole thing was, how does it know? See, if he's got an output that's not working right, and it's supposed to, a certain thing is supposed to happen, with the computer system or whatever. He said it had his Cadillac, for example, and it was I don't remember what year model it was, but people would bring, or the used car department would run vehicles through there. There was no all data back then. We didn't have shop manuals on anything but Fords and the Jeeps and Chryslers that we worked on. And so this Cadillac came in there, and when you went to operate the windshield washer light would just shine in your face. I mean, really, really bright. You may have seen them Cadillacs like that. And so he called me over there to this other mechanic stall in the shop foreman. He's the guy I'm always talking about that look and talk like Clem Pickens, only he wasn't as tall. And he says, how come this washer light comes on when you wash in the windshield? Because that washer fluid reservoir is full out there. And I says, well, I imagine that sensor is bad in that washer fluid reservoir. He says, but wait a minute, how come whenever I hook my test light up over here, I measure that, I hear something clicking. I said, I can't draw you a schematic of this, but I'm telling you, that light is only going to come on when you're washing the windshield because it's bright and in your face as it is. Nobody's going to want to see that driving on an interstate, you know, all the way from where to where. And so I said, so they're going to have it so that washer fluid is going to send us. He said, how does it know? And I said, there's a sensor in that washer, and it's going to tell you the system whenever it needs to turn on that light. It's just warning you that the washer fluid is low without having it on all the time, you know. And so he says, I said, so you have a bad sensor in that washer fluid reservoir. And he says, but how do I know that? I says, because I just told you. He snorted about that. Well, whenever the mechanic put the washer fluid reservoir on it, it took care of it. And the shop foreman didn't like that because he wanted me to be wrong. But his whole deal was, how does it know when to turn that light on, you know? So it wasn't too hard to figure out, really. So I gave him a helping hand. I checked the OBD1 connector on this Econoline, and I noticed there was a twisted data stream pair of wires present in the test connector. You can see where they are in this. And I says, okay. I said, you've got data stream on this. Because he had gone in there, and it was an AOD. And he had selected AOD, and the scan tool program was written so that if you got AOD, you didn't have data stream. But he had one of these weird ones that had AOD, but it also had data stream, which was an anomaly. You didn't usually see that. And I had run into this a couple of times, it seems to me like, or something, but I found out that if you look at that connector, regardless of what transmission or whether you've got mass airflow, and it's got data stream wires, they won't be dead. If those wires are there, that thing will have data stream. And he was basically shocked that he had data stream the whole time he'd been fighting with that thing. Because I used to actually use a meter with I made a long coat hanger that had a heat shrink on it except for the very end, and I could go into these wires from a distance and measure the voltage with my meter and all. But it took some doing to do that, and you had to know what all of them normally looked like, and you had to be watching them all the time if it was an intermittent concern and all that. And so he was just sort of bumfuddled because he'd been spoiled by data stream. Now, he spent years like I did working on vehicles that didn't have data stream, but on this particular one, he was flummoxed by that. So he did what I said, and there was the data stream. He said, I didn't know this. I've been fighting this the whole time. I didn't have the data stream. That's the new generation star tester there that we had. And sometimes, though, the scan tool doesn't work and we got to gather data using a scope. This wasn't one of those times. What we found was the throttle position sensor voltage gyrating a little bit above closed throttle. All right. It should held steady near flat and steady at 1 volt if you're not touching the gas, unless you're moving the throttle. Now, if somebody's fooling with the throttle, you know, but in this case, the throttle plate wasn't moving, so the airflow remained the same, but the engine controller was confused by the throttle voltage floating around, and it was causing the throttle. It was an in-range failure of the TP sensor, and it was causing all those extra accelerator pump shots I was talking about to go in there, and it was making it run rich as a dog. Now, it tended to clean up its act when it warmed up for some reason. I mean, the sensor probably did that for whatever reason. Now, when the PCM, I've told you about this before, when it gathers the closed throttle voltage, so it'll know when your foot's off the accelerator. But this is what that signal looked like. We didn't have a scope. This is what it would have looked like on a scope. Nobody was moving the throttle, but the engine controller just didn't know that. Now, had we not known that a floating TP signal would cause rich running, we might have overlooked this as the cause of the concern, because there was not a code for the throttle position sensor because it was an in-range failure. And that turned out to be troublesome and misleading because since there was no code, we didn't think to look in that direction. But knowing that throttle moving would cause it to run rich, inject extra fuel was very important. So that's why it's important to understand how and why fuel injection does the things that it does. Well, that concludes this presentation, and I hope you guys get something out of it. Tell your friends about it, share it with people, send me a like, make a comment, let me know what you think about it. And I'll see you guys next week. And hey, let's be careful out there.